Chapter 1 focuses on the basics of matter, energy, and measurement. Regarding matter, we want to be able to classify matter in a variety of different ways. First off, we can describe matter as either atoms or molecules. Atoms show up as a single element and just one part. Molecules are going to show up as at least a pair or more of atoms that come together. When those two atoms are the same element, such as in B here, we would call that a molecular element. So there are 7 that you need to know. We have hydrogen, H2, always shows up in a pair. We have nitrogen, N2, oxygen, O2, fluorine, F2. Then if you look at the periodic table, nitrogen is next to oxygen, which is next to fluorine. If we go below fluorine, we get chlorine, Cl2, bromine shows up as Br2, and iodine shows up as I2. These 7 are the diatomic elements, so naturally they show up in a pair, where other types of elements such as potassium, silver, lead, these all show up as a single atom. To get more complex, if I have 2 or more types of atoms in my molecule, then this is called a compound, and then I can mix all of these together to have a mixture. When we describe matter, we also can describe the state or the phase. There are 3. We have gas, notated by a G, liquid, notated by kind of this fancy L, and we have solid, notated by an S. This will describe how the matter is showing up in space. So ice, or a solid here, when we look at water, solid is very rigid in structure. It's going to hold its shape. The only type of movement that we have is vibrations. When we get to liquid, there's some more movement. So the molecules in general are spaced further apart, but they're still packed together. So here, solids are packed tightly. Liquids are still packed, but not as tight. They are not rigid, and they do not hold their shape. They can actually flow because there's movement. With vapor, or gas in general, so that was liquid. With gas, the molecules are far apart, so they're not packed anymore. Because they are far apart, they can also move around easily, making them able to be compressed if you decrease the volume, and also to expand if you increase the volume. Continuing to classify matter, we can determine if we have a sample, is it uniform throughout? If we can see different parts and it's not uniform, we call that a heterogeneous mixture. If it's all pretty uniform throughout and pretty consistent, it would be homogeneous. Now, if we look further in to that structure, we can ask ourselves, is it made up of all the same type of substance, or is it a mixture of a couple different substances? If it is a mixture, so made up of 2 or more different compositions, we would call it homogeneous mixture compared to heterogeneous. Homogeneous mixtures are made up of 2 or more substances, but you can't tell them apart when you zoom in. They're kind of all indistinguishable. Now, if it's all made up of only one substance, then it makes sense that it would be called pure. If that pure substance is just made up of one type of atom, then it is called an element. If it's made up of 2 or more types of atoms, and this is key types, right? So 2 or more different types of elements, then it's a compound. Now, when we talk about properties, when we measure matter and we're thinking about what type of property that sample has, we have 2 different types. We have intensive and extensive properties. So intensive, it means that this property is independent of how much sample you have. So I could have a big sample or a little sample. It doesn't matter how much I have, it has the same property. So an example of this would be density. right? If I have a sample of gold and another sample of gold, if it's gold, it doesn't matter if I have a big sample or a little sample, the density of gold is the density of gold. The boiling point or the melting point, or what color it is. If I have a big chunk of gold or a small little like gold nugget, they still have the same color. These types of properties help us to figure out what that substance is or identify it. Extensive properties are dependent. They depend on the amount of the substance you have. So if I have a big chunk and a little chunk, we can think, okay, mass, that's a property. Does my mass change if I have a big or a little amount? Well, we know the answer is yes. My big amount is going to have a larger mass. So same thing with volume and energy. So these are extensive and they depend on how much of the sample is present. Types of changes, we have both physical and chemical changes. Physical changes don't change the composition of the sample or the substance. When we see that, when that change occurs, like boiling or melting or condensing, it's still the same substance. We haven't changed the arrangement of the atoms. But chemical changes result in new substances. We get a rearrangement of atoms. And so because we have a new arrangement, we're going to have new properties because we have a new substance. When we make measurements, we use all types of units, but the SI units that are commonly used in science are length, which is the unit that we use is meters. The abbreviation is little m. Mass is actually in kilograms, and it's a kg. You might be wondering why one is a base unit of meters and this one is a kilogram. And that just has to do with how our units end up being grouped later on to make new, bigger, more complex units. Temperature we're going to use is actually in Kelvin, capital K. Time is in seconds. You could either call it SEC or S. And amount of substance is in moles, and we can abbreviate it with MOL. And we'll talk more about moles later. When we measure, we use lots of different tools. Some of the glassware we're going to use in lab, it involves a graduated cylinder and a burette. These are used to deliver a certain amount of volume that we want. We could have pipettes to help us deliver a smaller amount of volume. We could also have flasks to hold volumes. We're going to practice and use lots of different glassware so you can get familiar with it. Here are some of the metric prefixes. We already saw a kilogram, right? And so we saw a kilogram is 10 to the third grams or 1,000 grams. The ones that you really need to know are going to be from mega down to nano here. Really emphasizing, really emphasizing kilo, centi, milli, micro, and nano. And currently, as of 2024, the AP exam will provide these metric prefixes for you. Some measurements we're going to make often is temperature. There are 3 different temperature scales that get used. Commonly in our daily life is Fahrenheit. Most common in science is Celsius as well as Kelvin. So to go between these, Celsius is kind of our middle ground. That's where we're going to be able to go in and out of Kelvin and Fahrenheit. So to go to Kelvin, so temperature in Kelvin is going to be, we're going to take our temperature in degrees Celsius and we're going to add 273.15. If I want to get into Celsius from Kelvin, I'll subtract that. If I want to get temperature in degrees Fahrenheit, I'm going to take 1.8 times by my temperature in degrees Celsius, and I'm going to add 32 to that. So knowing these conversions will help us get in and out of our different units. And the top one is going to be the most common. Now, the scaling of Kelvin and Celsius is actually the same. So if I'm going from the melting point of water up to the boiling point, that's 100 degrees in between, in both Kelvin and Celsius. But because to go to Fahrenheit, we multiply by a factor of 1.8, we actually get a larger interval of that boiling between the melting and boiling point of water of 180 degrees. So it's a wider scale. Next thing we're going to talk about is density. Density is an intensive property of a substance. It's a physical property. We don't change the substance when we measure it. The units that we see for density most commonly is grams per milliliter or grams per centimeter cubed. Fun fact, a milliliter is a centimeter cubed. So those can be interchangeable in the future. Density is defined as the mass over the volume, or I like to consider it density equals love, which kind of looks like an M over a V. Here are some common densities that we'll see for substances. You'll probably end up just remembering that water has a density of 1, but you are not expected to memorize these. Regarding energy, there are 2 main types of energy, and most other types of energy can be classified as one of these. First off is kinetic energy, and this is the energy of motion. It depends on how much mass there is and velocity. So the kinetic energy is equal to 1/2 times the mass times the velocity squared. So I can have a high kinetic energy if I have a large mass and if I'm going really fast. Potential energy depends on a relative position. And relating to that, for chemistry, we'll even think of it as like composition and what is something made out of. And so regarding like bonds, we could also think of it as like a stored energy. So if I'm at the top of a hill, I'm not moving, I have a high potential energy because I have the potential to move very fast. Once I start to go downhill, my potential energy goes down because my height decreases, but I start to gain some speed, so my kinetic energy goes up. So there's that transfer of energy. Energy unit is joules. It comes from this combination of many different SI units. Kilogram meter squared per second squared. You don't need to memorize that, but that's just kind of where it comes from. And we can see that because if I take my mass in kilograms and times by velocity, meters per second, and I square it, those units come out. We just call it a joule. Commonly, we use calories, especially with nutritional labels. A calorie is 4.184 joules. And then the type of calorie we see on our nutritional labels is actually a capital calorie, and that's 1,000 little calories, or a kilocalorie. All right, next thing I want to talk about is precision versus accuracy. So when we make a measurement, or a series of measurements, precision is going to be how close those measurements are to each other. So I'm really precise if my darts all hit really close together. Accuracy is how close my measurements are to the correct or true value. So if we think about the dartboard, our goal is to hit the center. And so if I'm hitting the center, then I'm accurate. If I'm hitting off the center, I'm not very accurate. And experimentally, we're going to take of many different measurements, and because we can get multiple measurements, we can find the average and standard deviation. Now, the standard deviation is going to be related to my precision. The smaller my standard deviation, the more precise. And my average can be kind of related to the accuracy or how true it is. Depending on what device we're using will determine how precise and accurate we can be. So when we have a tool that has a lot of digits on the scale, then we're able to make a more precise measurement. But all devices have some degree of inaccuracy. So in the case of having a tool, when we're measuring, we're going to read the last digit. We're going to actually approximate the last digit. So if I look on, this guy again. My measurements here are between 5, so I have 25 and 30. So meaning I have to estimate, so I might do like 1, 2, 3, 4, 5, and I might estimate, oh, this looks like about 27, but somebody else might call it 26. And that last digit is my approximation, and but we still consider that reliable. But it might differ a little bit from a reader to reader.